Good morning, everybody, and thanks for joining us for today's webinar. We are seeing attendee number is still increasing. So let's give a moment for folks to join, and we will start the session momentarily. Okay, I see the number is still going up, so let's just give another minute or so, and we'll get meeting started. All right, so now it's 2 minutes past 11 and Eastern time. So the number I think is tapering off now. Let's just get our webinar started. Hello again, everybody, and welcome to the AHRI webinar session. My name is Xudong Wang. I'm the Vice President of Research at AHRI. Today, we are going to talk about hydrogen-enriched natural gas for heating products and the latest industry research related to it. So, hydrogen-enrichment offers decarbonization opportunities to our industry and our members. So, when talking about hydrogen-enriched natural gas, what would be some questions that pop into your head? What does it do to my furnace or water heaters at home? Or is anybody using it now? Or does it really reduce the carbon emission after all? So we will touch on all of them and plus many other points in this webinar. But before we start, I just want to have a couple housekeeping items. So first, this webinar is being recorded, and we will make the recorded session available online. And second, everybody is muted, so please use the Q&A button at the bottom of the screen for comments and questions at any time. And we will leave about 10 to 15 minutes or so in the end to respond to them. If we don't have enough time to respond all questions, and don't worry, we'll get back to you by email. So joining us today, our co-host, Stephen Memory, was A.O. Smith, and 3 other experts who have been closely working with AHRI on the hydrogen-enriched fuel-related activities. So Stephen is a member of the AHRI Research and Technology Committee and the chair of the AHRI working group guiding the hydrogen-enriched natural gas project. So Stephen, welcome. Would you give us a quick rundown of what we cover and who our speakers are?
Yeah, okay. Thanks, Xudong. And yes, I'm here in the capacity as being the chair of one of the projects that you're going to hear about today. I think we've all seen the exponential increase in activity over the last year or so in both hydrogen and hydrogen natural gas mixtures, as a way to reduce carbon intensity of the products of combustion. And so I think AHRI put a fantastic webinar together for you this afternoon, and we have 3 very, very well qualified speakers. The first one we're going to hear about project 8024 that was funded by the R&T committee of AHRI, and that was conducted by Enertech International out of the UK. And I'll introduce Paul Needley, who's the managing director there, in a minute. We're then going to have a presentation by Josip Novkovic of CSA, and he's going to talk about appliance and equipment performance with hydrogen-enriched natural gases. And then finally, we're going to hear from Ted Williams from the American Gas Association on hydrogen-enriched natural gas appliance activities, what they're doing in this area. So I'd just like to introduce briefly the three speakers. Again, Paul Needley, he's the Managing Director of Enertech International Limited. Enertech is actually the UK's largest independent engineering R&D consultancy, specializing in the design, development, and certification of energy-consuming products. It operates worldwide, and Paul liaises with clients, trade associations, and government bodies in the development and commercialization of new products and technologies. Paul joined Enertech in 1987, initially as a research engineer, then project manager and director, prior to assuming his current role as managing director in 2016. So we'll hear from Paul, who's got a lot of experience in this area. We're then going to hear from Josip Novkovic. He's the program manager for fuels and appliances at the CSA Group. He's been with the CSA Group for 14 years in various roles in both standards and testing and certification. He leads the program's strategic oversight and management of North American activities to support development of codes and standards for gas appliances, systems, equipment, and components in residential and commercial applications. And then finally, we're going to hear from Ted Williams. He's a Senior Director for Codes and Standards at the American Gas Association. Very familiar name. So Ted is a Senior Director at AGA, where he leads the natural gas end-use codes and standards activities, including providing AGA members with technical expertise on natural gas quality, including hydrogen and gas properties. Ted has been participating in codes and standards development activities since he joined AGA back in 1997, where he also serves as staff liaison to Building Energy Codes and Standards Task Forces on energy conservation, research, indoor air quality, and model codes. So I think you'll agree it's a very, very well-respected panel that we have here this morning. And I think if we can go to the next slide, Shudong will start, yes, we'll start going on with the project 8024, which was funded by the R&T committee. It was started about a year and a half ago, and it was carried out by Enertech International, with Paul Needley leading it, on behalf of AHRA, to basically validate whether North America gas appliances remain safe if they're fueled by hydrogen-enriched natural gas. The report has been completed and submitted to AHRI, and you're going to hear a summary of that report that you see there on the right-hand side today. Again, the objective basically was to assess the uncertainties and safety implications of a hydrogen-enriched fuel in both factory, i.e. new, and currently installed gas-fired products and components manufactured by AHRI members. The scope covers new, existing, and old, i.e. legacy gas-fired products, and essential components such as valves, pipes, and corrugated stainless steel tubing that connect the equipment to the supply line. And specifically, the equipment assessed includes furnaces, boilers, burners, control valves, venting products, water heaters, and pool heaters. So it's an extensive study. And I think with that, Paul, I will pass it over to you.
Okay, thank you very much, and good morning to you all. Thanks for your kind introduction, Steve. I'm delighted to have this opportunity to speak about the work we've been privileged to undertake on behalf of AHRI, although in an ideal world, I'd rather have done this in person instead of via a screen. Once the COVID pandemic subsides, climate change and the need to decarbonise is likely to be the next topic to dominate the news. and hydrogen is seen worldwide as the best way to decarbonise the gas supply, either by blending it with methane or even replacing methane in the longer term. Now, it's probably fair to say that Europe, and particularly the UK, is at the forefront of the drive to decarbonise, and consequently, perhaps for a change, North America can reflect upon what is happening elsewhere, take note, check the science, and apply the knowledge gained to get the best solution for the North American market. And hopefully, this project provides information to facilitate that opportunity. Next slide, please. Thank you. So the rationale behind the project was to look at what information is currently available, to refer to the science, specifically combustion technology and thermodynamics, and apply this to typical American gas appliances so that we could identify and evaluate risks, then propose what, if any, action is required. The slide shows the structure of Enertech's report. And in compiling the report, we've tried to produce a state-of-the-art working document valid at the date of publication. It's not possible to cover everything in one report, and new information is becoming available on a rolling basis. But the report contains many links to reference documents and projects around the world, and it can be used as a reference document in itself and as a link to everything you may need to find relating to the subject concerned. Next slide, please. Thank you. Amid the news and hype about hydrogen worldwide, many of the projects underway are concerned with the production, storage and distribution of hydrogen. And whilst these are very important and essential if hydrogen is to become mainstream, we are concerned with its end use. Even then, there are questions over its best use. Should it be used for industrial applications, for power generation, or transport, rather than for heating or cooking? However, natural gas combustion produces CO2, and for the gas network to survive, it needs decarbonising, and hydrogen offers the best way to do this in volume, and of course, our project focuses on heating products. Whatever the product or wider use of hydrogen, the challenges are the same. Safety issues and concerns have to be priority number one. Technical challenges need to be overcome, and there needs to be a viable business model for it to succeed. Next slide, please, Sudan. Thank you. In June 2019, the UK government passed legislation to make net zero by 2050 a legally binding target. Decarbonisation is therefore a key policy, and hydrogen is seen as the only viable way to continue to operate a major national gas grid in the longer term. In November 2020, the Prime Minister Boris Johnson published a 10-point plan for a green industrial revolution. And his point number 2 is driving the growth of low-carbon hydrogen. Points 1, 7 and 8 are also relevant to this study, advancing offshore wind, greener buildings, and investing in carbon capture, use and storage, respectively. Now, essentially, the Prime Minister's plan is to start blending hydrogen into the UK gas main from 2023, and at the same time have trials for 100% hydrogen heating of homes. Investment in excess wind power and carbon capture and storage to extract hydrogen from methane will produce the hydrogen to facilitate this. HydroPloy is the UK's first practical project to demonstrate that hydrogen can safely be blended into the natural gas distribution system without requiring any changes to appliances. The site chosen was Keele University campus, which is located in the West Midlands. The objective of the HydroPloy project is principally to develop the initial evidence base that hydrogen can be blended into an operational natural gas network without disruption to customers and without prejudicing the safety of end users. Now, interestingly, in parallel with the main report, major boiler manufacturers have supplied 2 identical boilers for testing. At least 8 boilers in total are on a marathon test rig, half of which have been fired on methane, and the other half on blended methane and hydrogen at up to 20%. Now, at the end of a 12-month test period, these boilers will be returned to the manufacturers for evaluation, and the manufacturers will not be advised which one was operating on natural gas and which one was operating on blended gas until after the manufacturer has finished their assessment. And the purpose of this is to determine whether the boilers operating on the blended gas deteriorate faster than the ones on methane. This is perhaps the most important feedback from this project and will be of interest to all manufacturers if the results are made public by the manufacturers concerned. And then upon completion of the tests at Keele, and they have just finished, further large-scale trials are planned on public networks in the northeast and in the northwest of the UK very soon. The BEIS HyFleet project, BEIS being the UK Government Department for Business, Energy and Industrial Strategy, aims to establish whether it is technically possible, safe and convenient to replace natural gas with hydrogen in residential and commercial buildings and gas appliances. This is specifically aimed at 100% hydrogen and involves many of the leading manufacturers and component suppliers in the UK and Europe. The project commenced in 2018 and is due for completion in a few weeks' time, with the expected outputs being a range of EC certified domestic and commercial appliances suitable for sale in the UK. And initially these appliances will be used to feed into other hydrogen projects. Enertech International are heavily involved in this project. Indeed, we're developing 16 separate hydrogen appliances and will be pleased to provide AHRI members with updates or more details upon request. The H21 Lead Citygate project was a study carried out in 2016 with the aim of determining the feasibility from both a technical and economic viewpoint of converting the existing natural gas network in Leeds, one of the UK's largest cities, to 100% hydrogen. This project is focused on upstream of the appliance. And following the success of the original H21 project, several follow-up projects have commenced and are ongoing under the H21 banner. SGN's H100 project is to construct and demonstrate the UK's first specific network for 100% hydrogen. And assuming this is successful, there are plans for larger networks to follow. This should be starting later this year. Next slide, please, Sudan. Thank you. I'll try and go through this fairly quickly, but Germany, this is just an international summary of what we think is happening. During 2020, the German government adopted a new hydrogen strategy and devoted €8 billion, or $10.5 billion, for investing in making hydrogen a marketable fuel. Germany has declared that only hydrogen produced from renewable energies, or green hydrogen, is sustainable in the long term. And at this stage, it's not clear whether distributed gas will be blended or ultimately 100%. Nor is it clear how much resource will be spent on hydrogen for heating, but Germany is already strong on support for fuel cell heating systems. In the Netherlands, there's a TKI new gas programme, that's the Dutch government's programme to stimulate innovative applications of gas. They published a hydrogen roadmap in 2018, which describes how sustainable hydrogen can be embedded into the Dutch energy and raw materials system. In Belgium, Belgian organisations including Marco Gas, an industry association who are based there, are active in hydrogen projects, but we don't have any information specifically relating to trials in Belgium at the moment. In Italy, Snam, a distribution company, is to test a 10% blended mix in southern Italy and currently running a 5% mix in an area near Salero. Canada, Natural Resources Canada released their hydrogen strategy for Canada in December 2020. Title Seizing the Opportunities for Hydrogen, a call to action. The 104-page document covers all aspects of hydrogen and states Canada's opportunities to produce, use and even export hydrogen. And the article concludes that blending at a lower level is technically feasible today, and by 2050, hydrogen could account for 86% of the gas supply by volume. In Australia, a government report states that the Australian Gas Infrastructure Group are investing $11.4 million in a demonstration hydrogen park project and injection into the local gas supply. Initially 5% mix, but looking to go to 10% soon. And there are several other projects in Australia. Japan, although interested in hydrogen for vehicles and fuel cells, we're not aware of any other interest in using hydrogen for heating, apart from fuel cells. And South Korea has a clear policy directed towards hydrogen, but aimed at vehicles and fuel cells only for heating. No mention of boilers or admixtures at this stage. And then the United States, well, although this is covered in our report, and particular thanks to Professor Vince McDonnell for his contribution, I do not feel qualified to talk to you today about your home market. So Ted Williams has kindly offered to help out here. So thank you. Please, Ted.
Yes, well, thank you, Paul. Very quickly, in line with the other country descriptions, in the US, there's a roadmap document that was produced in 2019, I believe it is, it'll be continually updated by US Department of Energy that covers the plans from the federal government perspective for hydrogen in the US natural gas system and in specific applications of hydrogen for power generation and the like. Not a lot of emphasis really on end-use applications that we're talking about here, but that's the government role. One other activity is called the Low Carbon Research Initiative that has been essentially led by the Electric Power Research Institute, with the Gas Technology Institute in Chicago being a primary technical contributor, a very widely sponsored effort to look at low carbon solutions, including power to gas and hydrogen applications. That too is although it's a very large program, the applications really for end use equipment in residential and commercial markets fairly limited and sort of a late addition to the program. In both cases, the LCRI, Low Carbon Research Initiative, and the DOE activities really deal mainly with upstream production issues, supply issues, and transmission and distribution issues, not so much on end use equipment. So I think that's probably all I can add at this point. Thanks, Paul. Back to you.
Thank you very much, Ted. Next slide, please, Sudong. Thank you. So, literature review. We conducted a review of available literature from many sources. A list of references is included at the end of this presentation and, of course, in the report itself. The study involved papers from individual professional publications, industry body reports, and published project reports concerning hydrogen admixtures. I don't propose to describe this section in detail. Indeed, much of the output feeds into the next section. But I do want to draw attention to the European research project called TIGER, standing for Testing Hydrogen Admixtures for Gas Appliances. This project sets out to develop and communicate a detailed understanding of the impact of blends on natural gas and hydrogen on end-use applications, specifically in the European domestic and commercial sector. This is a little bit like the UK high deploy program, but done on an even bigger scale. Next slide, please, Sudong. So looking at the theory, this graph issued by Marco Gas shows the Wobbe number, the blue line, is remarkably constant as the percentage of hydrogen and methane increases despite a significant fall in calorific value, that's the red line, and the relative density, the grey line, plotted against the right-hand side axis. This means that the heat flow through pipes is very similar with pure methane and pure hydrogen and anywhere in between it. Consequently, pipe sizing is not an issue at any concentration of hydrogen unless the pipework is right on the critical limit. Next slide, please. Thank you. This graph from the TIGER project shows that despite pure hydrogen, the grey line, burning with a higher temperature than pure methane, the blue line, at all aeration levels, an admixture is biased towards the methane. The blue line shows a 50-50 blend, and clearly it is not halfway between the other two lines. So by deduction, a 10 or 20% blend is going to be fairly close to the combustion temperature of methane, especially at excess air levels where most gas appliances operate. Next slide, please. Thank you. Hydrogen requires less air for combustion than methane does. Consequently, as the blend of hydrogen increases from left to right, the air requirement, that's the blue line, reduces roughly in proportion to the calorific value, either net or gross. This graph was produced by the TIGER project. Europeans tend to use net CV, whereas we, like you, tend to think in terms of gross CV. Next slide, please, Sudong. Thank you. One of the key concerns with admixtures is the propensity to light back due to the flame speed of hydrogen being much higher than that of methane. Lightback is likely to happen if the flame speed is higher than the velocity at which the gas passes through the burner ports. There are other factors such as flame quenching which can prevent this, especially on premix burners, but in simple terms, burners are designed with flame ports being the correct size to support the required flame. So if the flame speed increases, as it will with a hydrogen admixture, the flame front will move towards the burner ports. For a given burner design and heat input, the exit velocity through the ports can be calculated, providing the level of aeration and the temperature of the air-fuel mix is known. Now, this graph represents a typical North American burner with a 50% primary aeration, atmospheric burner that is, and shows the relationship between burner port velocity, that's the blue lines, and flame speed, orange lines. The solid lines represent natural gas or methane, and the dotted lines represent a 20% hydrogen blend. So although the two sets of dotted lines are closer than the solid lines, there is a clear difference between the flame speed and the port velocity. So in this example, there is no chance of a light back. And should the flame light around during ignition, another possibility is it is likely that the flame would clear itself under these conditions. And next slide, please, Sudong. Thank you.
Paul, I'm sorry, Paul. I just got a message from one of the audience and said that the slide does not advance. I just want to make sure it's not from our end. Can anyone from the audience just tap through chat say it works or not? Okay, it seems like works for most of folks. Thank you so much. Sorry, Paul, go ahead and continue. Sorry for the interruption.
Okay, thank you. Right, yeah, I can see the slide here.
Okay.
There's not enough time today to talk through all of the theory, but in summary, I can state that with a hydrogen admixture, depending upon the blend, flame speed is likely to increase slightly, thermal radiation will decrease slightly, thermal efficiency will decrease slightly, mainly due to the higher excess air. NOx emissions may decrease because of the higher excess air. The dew point will fall very slightly. Flame detection used in flame ionization becomes unreliable above around 30% hydrogen. Flame colour is not an issue at low blends, and soundness is slightly more difficult to maintain. Safety depends upon all other factors falling into place, especially resistance to lightback. Next slide, please, Zudong. Thank you. Although test work was technically outside the project brief, we took an opportunity to test a traditional American atmospheric burner with slotted ports rather than circular ports to determine the effect of a 23% hydrogen blend, which we keep in stock as a European test gas. And the graph shows the effect on burner temperature of changing from methane to 23% hydrogen after 750 seconds of operation. So a significant increase in temperature, approximately 72 F, can be seen as a result of changing the gas. And we also tested the burner for lightback, and as predicted by our calculations, lightback did not occur with either gas. Next slide, please, Sudan. This slide just shows the products assessed in this study, which Steve already alluded to. So if we can continue on to the next slide, please. Thank you. I've just got some facts. Yeah. Potential leakage from joint. Mixed up in my notes here. Potential leakage from joints and components is because hydrogen is a smaller molecule and more likely to leak out of joints than methane is. This should be borne in mind in terms of installation. Also, when installing an appliance, it's very important that no adjustments are made, because any adjustment, the automatic effect of a 20% blend is a 5% down rating. I didn't mention that earlier, but the 5% down rating that you get automatically because of the different characteristics of the gas is useful in offsetting potential temperature increases, which would occur if the appliance was adjusted to restore 100% of rating. So adjusting the appliance to compensate for the down rating may invalidate the certification, which is based on methane, because it would be overrated if it was then used on methane. A further complication is that the installer would have no means of accurately measuring the blend of hydrogen at the time of making the adjustment, so therefore the setting would be unknown. Changing the fuel type will have an impact on combustion performance, but there are other anticipated challenges which will also affect combustion, such as the changes in flame shape, available aeration and updraft. Any increase in combustion products temperature could lead to higher ambient temperature for components and materials, which could potentially exceed the designated limit for safe contact for users or durability issues. And due to the changes in the flame characteristics, such as positioning and temperature, coupled with the expected down rating of 5%, it's expected that the thermal efficiency could be very slightly affected, not significantly, as the various components compensate for each other, as mentioned earlier in the report. In terms of combustion byproducts, with blended hydrogen being consumed, there will be an increase in condensate production, and the disposal system will need to be assessed for suitability. There will also be an increase in hydrochloric condensate waste, which could be incompatible with existing disposal line materials. Pure hydrogen produces about 40% more water vapour than methane, so a 20% blend is likely to produce about 8% more condensate. But this can vary depending upon conditions and the dew point. So in practice, the additional condensate may be up to 20%. For any given heat input, with an increase in the temperature of combustion products, it's expected that there will be more updraft generated in atmospheric appliances, which could further contribute to flame lift from the burner. In terms of particular product types, what I've said so far really covers all appliances. As far as furnaces are concerned, long-term durability of components could be affected by any increase in flame temperature and condensate. Any furnace heat exchanger welds that are situated above the burner could be subject to increased temperature and condensate and could potentially be susceptible to leakage. And equally, during operation of furnaces, there is a potential that the increase in combustion products temperature could also lead to long-term durability issues and subsequent cracking. Furnace heat exchangers that overheat frequently are sometimes known to prematurely fail, and there's a potential for that to happen with a greater extent here. There is also a potential risk of hydrogen embrittlement, especially if there are any welds in the heat exchanger at that point. In terms of boilers, same applies really regarding welds inside the heat exchanger. Could be vulnerable in the long term, especially if stainless steel and is exposed to any unburnt hydrogen, potential risk of hydrogen embrittlement. In industrial boilers, the shell and tube design, there will be less radiation heat transfer in the combustion chamber due to the low radiation emissivity from a hydrogen flame, very diluted with a blend of 20%. But in theory, this could result in higher backplate temperatures and more heat transfer in the secondary tubes. This could overstress different parts of the heat exchanger and lead to non-optimized performance or even premature failure. In terms of burners, where burners are commissioned on site, the installer should commission the appliance as though the gas supply is 100% methane. This would be expected to facilitate the normal 5% down rating, which offsets some of the potential problems with higher temperatures. If the commissioning engineer knows the hydrogen blend in the gas supply, there is a possibility that they may be able to adjust it to compensate for the down rating, but this should be avoided for the reasons I've just mentioned. We don't want any overrating or increased temperatures. Likewise, with the increase in temperature, condensate production, deposition, atmospheric, with a lower dew point, atmospheric burners in particular may become more susceptible to corrosion, which could affect the long-term durability. In terms of control valves, mainly potential leakage through the valve seats and compatibility with hydrogen. Not only due to the small molecular size of hydrogen, it is possible that the hydrogen element of the blended gas could sink through the valve seat and possibly affect any materials that haven't been approved for use with hydrogen. Whilst this can be assessed for future production valves, legacy valves, especially those operating for a number of years, could be subject to aging of seals or mechanical wear, and appropriate pressure testing should be carried out when blended gas is used instead of methane. For venting products, long-term durability will need to be verified under the new temperature conditions, especially for designated condensing systems with the extra hydrochloric condensate waste to ensure that ducts don't begin to leak products over time. The potential for hydrochloric acid formation is increased due to the greater presence of hydrogen molecules, but in practice any change is likely to be minimal. Operation, again, we've mentioned slight increase in condensate production and potentially temperature. Products of combustion in commercial and industrial vent systems with separate condensate drains, the sizing of the drain will need to be revalidated to make sure they're able to cope with the extra increase in production, condensate production. In terms of water heaters, many water heaters have a straight vent that is situated across the top of the burner. Due to constant condensate buildup on the inside of this vent, this can lead to condensate dripping back onto the burner, causing hissing noises during operation. Slightly greater propensity to this with the extra moisture content in the blended gas and the lower dew point, slightly lower dew point. And welded water storage tanks that are situated above the burner may be increased to increased temperature or condensate. And really what I've said about combustion byproducts in vent systems applies equally to water heaters as it did in the other appliances. Pool heaters, similar as to what I've just explained, but pool heaters are often situated outdoors, in which case hydrogen seepage through joints exterior to the building are less of a concern due to the inability to build up in a contained area. But the additional water vapour could cause a nuisance if it visibly pools adjacent to the appliance on non-condensing models. And stainless steel, or steel pipe fitting, specifically corrugated stainless steel tube, with any blended hydrogen methane gas molecules will be in contact with the tube walls. Hydrogen brittlement is considered unlikely, but possible, even at room temperature in some materials, although only if it's highly stressed. SST is not particularly stressed in operation. It's got low gas pressures, its susceptibility to embrittlement is unlikely to cause a problem. However, specialist metallurgical advice should be sought before commercially marketing CCST for use with hydrogen. And care should be taken not to overstress the vents when installing it. Next slide, please, Sudan, thank you. Difference between North American and European appliances. Well, obviously there's market requirements. The market requirements are slightly different, mainly based on the application and use of appliances rather than technical differences. We tend to have smaller properties, so the appliances tend to be more prominent. And boilers, for instance, are usually installed in the kitchen area rather than the utility room. However, there is a significant difference in certification requirements, because in Europe we have specific limit gases which represent the extremes for what could be encountered in the gas network. We have G20, 100% methane for a reference gas. And then we have three limit gases, G21, 222 and 23. They have it's natural gas with 13% propane, 23% hydrogen and 7.5% nitrogen respectively. The propane content is for a combustion limit gas, the nitrogen content is for a lift gas, and the hydrogen content is a light back limit gas. That means that all appliances on the European market have been tested for ignition with 23% hydrogen. Furthermore, old British standards before we joined the EU, that's before we joined the EU, before we left the EU, they used to test to a test gas called G22, which had a 35% blend of hydrogen, as opposed to the 23% blend that we use now, which means that legacy UK products are even more resistant to light back because they were tested with a higher limit gas. Now at Enertech, we're often contacted to gain European certification for North American clients wishing to enter the European market. And several years ago, we did this for a pool heater manufacturer. And unfortunately, it miserably failed the light back tests. And the only way we could solve it was to change the burners to European style. Not a problem then, but if any of these are still installed and working as legacy appliances, there will be issues when supplied with a blended gas, because at 23% it just lit back straight away. Very big burner ports. Just a few alarm bells going there. Next slide, please, Sudan. Thank you. I'm conscious of time, so I won't go through the FMEA process, fairly standard process, and the output is summarised in the report. There's a separate summary for each product type that we looked at, and there's details available in a separate file from AHRI upon request. Next slide, please, Sudan. Thank you. As part of the project, we've developed a light back calculator. This is based upon manufacturer. It's available to members from AHRI upon request. And basically, if a manufacturer inputs the heat input, burner port area, CO2, and temperature inside the burner, the output will be, it'll calculate the excess air factor and velocities, etc. And ultimately, it will give you a message indicating the risk of light back. There's an example shown on the screen there. I don't suppose you'll be able to read it on the slide, but it basically says whether there's a danger of light back or not for that particular appliance. Next slide, please, Sudan. Thank you. Just need to script. So, conclusions regarding performance. A reduction in heat input of approximately 5%, an increase in combustion products dew point of approximately 2 degree F, an increase in flame speed, reduction in radiation heat transfer, higher excess air level, likely reduction in NOx, an increase in burner temperature, and an increase in water vapour. And the practical effect, the low heat input coupled with an increase in excess air presents a significant increase in flame temperature and can cause a reduction in NOx. The effect on efficiency depends upon the appliance design and the relative counterbalancing of characteristics, but the lower heat input marginally increases. The lower heat input marginally increases efficiency, whereas the higher excess air and low radiation marginally decrease it. Right, next slide, please, Sudan. Thank you. So I'll just get out of step here, some notes. So if the appliance is adjusted to recover the lost 5%, the counterbalancing effect is lost. NOx, flame temperature and burner temperature all rise and efficiency is likely to fall. Long-term reliability issues are not known. Flame lightback is a concern, especially on legacy appliances. Hydrogen embrittlement is a concern, but initial results from the THIGA project suggest it does not pose a threat to gas appliances under normal conditions. However, its components and risks need to be understood with respect to the whole gas network, not just gas appliances. And hydrogen is more volatile than methane and carries a higher risk of detonation if mishandled. I'm running short of time, so I'll move on to the next slide, please, Sudan. Thank you. So our overall conclusion is that subject to conducting further research in the key areas defined in this report, theoretical indications and initial evidence suggest that it should be safe to inject up to 20% hydrogen into the US gas main without significant risk. Next slide, please, Sudan. Thank you. So North American appliances and installations are sufficiently different to overseas products to require separate consideration and research into the long-term and reliability effects of blended gas. I think international cooperation could have mutual benefits. Legacy appliances are a concern and a policy is needed, perhaps involving an on-site risk assessment, and perhaps the lightback calculator could be used on-site for appliances that are unknown. Consider blended hydrogen as an intermediate step and evaluate the possibility of 100% hydrogen in areas where this might be feasible. And that takes us to the next slide, please, Sudan. 100% hydrogen. Well, the UK High-for-Heat project is demonstrating that hydrogen appliances are feasible. By mid-2021, we will have certified hydrogen gas fires, boilers, hobs, ovens, grills, furnaces and commercial catering equipment available for sale when or if a hydrogen market exists. Hydrogen-ready appliances are seen as the future here, likely to be mandatory in the UK from 2025. That means that they are supplied suitable for methane, but are convertible in under an hour by a competent gas engineer. So when hydrogen is installed in the local area, you don't have to replace the appliance, you simply get it converted. And many other countries are following similar paths. Next slide, please, Sudan. Thank you. And finally, just our view. We've developed 16 different hydrogen appliances in the High-for-Heat programme, working with manufacturers in a consortium approach. Development time can be shortened with the use of modelling tools and techniques, and there's just an illustration there showing what our CFD engineer predicted before we fired the sample, and the actual flame was on the left is what we achieved, which we're quite pleased with that. And we haven't found a European production gas appliance that cannot be adapted to operate on 100% hydrogen. Next slide, please, Sudan. And well, finally, that's just a review of the literature references. They're all in the report together with the appropriate links. So I'm sorry I've rushed through this a bit. I'm very conscious of time. I hope that gives everybody a flavour of it. If you want any more information from me, please, there's a question and answer session at the end of this session, or contact me by email afterwards. And thank you very much for listening.
Yeah, Paul and Stephen, thanks for the excellent overview of the project and the key takeaways. And I think the point is, you know, everybody is encouraged to look through the report, and the report has a lot of the details, and you can download the report from our website. And I think also in parallel with this theoretical analysis, and AHRI also has been working closely with our friends at the AGA and the CISA on a exploratory testing program. So I guess the next two speakers will talk about the testing. So Yusuf and Ted, thank you for coming, and please let us know what we have jointly tested and what results we actually found. So yeah, thank you.
Great, thank you, Judong. Appreciate the time today and appreciate the opportunity to present to the group. As mentioned before, I'm Program Manager for the Fuels and Appliances Standards Program here at CSA Group, and Ted Williams is going to join me today, Senior Director of AGA or at AGA, to help present the results. Next slide, please. So through a presentation, we'll touch on a few things, overview of CSA Group standards and our research program. We will cover the hydrogen-enriched natural gas research project, including the origin and objective of the project, the research project plan, and deliver some of the preliminary summary of results. And then we will conclude with some next steps and future work that CSA has been coordinating with industry stakeholders. So at CSA, we take a comprehensive approach to standards development. We engage in leading edge research, help inform the standards content, the committees that we work with, also providing training, education of products to ensure that the standards that are being published are used correctly, and to help ensure the comprehension and application of the standards that we publish. The presentation, again, will focus on a research project that was intended to provide data, inform future standards development activities around the topic of hydrogen-enriched natural gases. So at CSA Group, we believe in keeping pace and even getting ahead of change, and that relies heavily on a research program. We've dedicated considerable efforts over the years to conducting and supporting that research that focus on new and emerging areas, support the development of future standards and codes development, providing interim guidance to industries on the development and adoption of new technologies, and demonstrating our ongoing commitment to social good. At the bottom of that, of this slide here, there is a link to access all the reports that have been published over the last couple of years, which includes 60 plus. And again, this presentation that's focusing on the hydrogen-enriched natural gas project will also be available through the CSA website in the coming months. So turning over to the details of the research project, this was a research project, as mentioned earlier, that was co-funded by the Air Conditioning, Heating, and Refrigeration Institute, American Gas Association, and CSA Group. And appliances were donated by AHRI members as an in-kind contribution. So we're going to touch a little bit on the project outline and the objectives of this. And as many of you have already heard today, due to the various government policies, industry is looking at making efforts to identify approaches in decreasing its environmental impact. And one of those approaches that was recognized is introducing renewable gases into the North American natural gas system and potentially blending hydrogen with natural gas. Proposal was received and considered to do an exploratory study assessing performance and safety of select appliances containing up to 15% hydrogen blends with methane. And that was initiated to better understand the impact and support future standards development activities. And I won't emphasize enough that this was an exploratory program, so you'll hear that word consistently used throughout the presentation today. But the exploratory program was not intended to offer any conclusive results, but was really meant to offer a baseline for potential future work. At the onset of the project, a project advisory panel was formed consisting of the co-funders and AHRI members to support establishing the project plan and scope. And really the project plan was broken down into three main phases, and it was really including a literature review, selection of the appliances, and selected tests from the applicable CSA and ANSI standards. So the literature review was really the first step, and it was meant to identify how the vendor was going to approach the concept of hydrogen-enriched natural gases. So as many of you probably know, design and performance of residential appliances are dictated by combustion energy output, fuel gases, currently including conventional natural gases, and obviously those variants to those conventional natural gases. So when compared to natural gas, hydrogen has a lower specific gravity, lower heating value by volume that results in the hydrogen-enriched natural gas WOBE index in a lower, hydrogen-enriched natural gas WOBE index than that of natural gas. Although the WOBE index is determined to be, in essence, the best single parameter measure of gas interchangeability, a simple comparison of the WOBE number was not a reliable predictor of the hydrogen-enriched natural gas uses in the residential appliances for really three main reasons. The Bowlby number of the hydrogen-enriched natural gas is nonlinear changes with the hydrogen content. The Bowlby index cannot completely predict gas interchangeability as it does not account for all combustion phenomena. And the Bowlby index and higher heating value generally refer to a burner performance, but not the appliance operation. So the vendor, instead of simply relying on the interchangeability factor and concluding that the 15% hydrogen is not an issue, according to the Bowlby number, the vendor actually evaluated the appliance behavior with use of different gases to come to that conclusion. And using the gases that are not compatible with appliances design may potentially cause many issues, such as incomplete combustion, therefore increased level of emissions of carbon monoxide, and decreased efficiency and lifetime of the appliances. Next slide, please. So we're going to outline here real quickly the products that were selected. And really the products that were selected were based on discussions with the project advisory panel and the vendor to get as broad of a selection as possible, but understand that there were constraints on the scope of the project, including equipment availability, timeframe, and cost. So the focus of the project was on space heating and water heating appliances, which included those listed there: the residential four units of residential warm air furnaces, 4 units of boilers, 2 units of water heaters, and 2 space heaters. Towards the end of the project itself, we received a proposal where we included household piping, and the household piping materials that were supplied and provided for the testing was black iron steel pipe, press connect copper, flare connect copper, and corrugated stainless steel tubing. Next slide, please. Thank you. So similar to the products that were selected, tests were also selected based on discussions with the project advisory panel and the vendor. Again, however, understanding the limitations that we face with choosing the products, there was only a select set of tests that were being selected and chosen. And really those tests were being considered and chosen based on the products selected and what initial results would be most impactful for future studies. And they were performed through the methods outlined in the binational CSA ANSI Z211 series of standards. So next, Ted will provide an overview of the results of the testing. Ted, over to you.
Sure, thanks, Joseph. Just a couple comments before we get into the summary of the results. Keep in mind that we've got 2 presentations today, one based on mainly on theoretical considerations and some other experience from overseas, and then the test that we're talking about here. There really hasn't been any attempt to sort of coordinate our presentations. You may find that consistency in some of our findings with the theoretical predictions that Paul described, which I think is very important, and some additional field or essentially testing results that are similar as well. But again, there are some other issues that need to be discussed and more completely vetted as we move forward and we talk to each other. And that international coordination effort that Paul mentioned, I think, is very important to that end. And I think that we need to make sure that we understand that this is exploratory and that we really looked at going into testing without any real hypothesis to be tested during this testing process, but instead make sure we apply what we thought were relevant tests out of the standards for safety that CSA group maintains for North America, both Canada and US. And look at the performance requirements as appliances are currently tested under those standards for safety. So it's not the be all and end all for evaluating appliances operating on hydrogen, but it is a basis for a starting point for looking at how appliances might respond under the certification testing to hydrogen. What I'm going to show are just some samplings of the results that are produced by the testing. There's much more to describe that will be shown in the final report when it comes out. We're very much towards the end of completing that report and going through review of the report. But just to start with, the principal conclusion from the testing was that we didn't observe in the tests across the 4 categories of appliances tested in the combustion performance any operability issues related to safety concerns in the operation. And this refers to basic ignition issues, burner operating characteristics, including liftoff and what Paul calls light back, we call flashback. So excuse my terminology change. But in any case, we didn't see anything that was critical from across the appliances. It was evidenced in the tests that were performed. In terms of emissions, we didn't see any real excursions in either carbon monoxide or NOx production that really exhibited any definable trends. And excursions, I mean really trends. As you see, look at the plot shown here. You'll see differences, of course, going from pure methane, which is the baseline gas, to methane blends with 5% hydrogen and 15% hydrogen in methane. And you'll see differences certainly, but you don't see any monotonic trends. You'll see the numbers bounce around quite a bit. And with respect to the furnaces shown in this plot, none of these are ultra low NOx products, and so you'll see the NOx numbers in air-free basis. They may seem high compared to those ultra low NOx California performance, if you will, appliances. The only ultra low NOx tests that were performed were done on the storage water heaters. I think we had one model that was ultra low NOx, but the rest were conventional appliances. But anyway, that's what we're sort of seeing, and you'll see across the furnaces shifts that vary depending on the blends and in terms of the numbers with ppm air free. And the same was true for CO, and the same was true across the other products tested. With respect to controls, we didn't find any issues with respect to changes in density that modified the control operations for the appliance. We didn't find any leakage when they were tested both for manifold pressure changes or bubbles generated in the water bath in the form of leakage based on essentially the interior to the appliance piping and tubing that's used. We did not see excessive changes. Oops, we slipped ahead. You go back one slide. There you go. Excessive heat exchanger temperatures on the equipment. We did not see from either the air-to-air heat exchangers or to boiler tubes. There was one issue that will come up a little bit later in terms of looking forward with respect to stability of pilot, showing one of the two invented space heaters tested, and we'll come back to that. That was one issue as far as the maintaining pilot operation that has some larger implications beyond pilots that we'll talk about a little bit later. Next slide, please. In terms of the input effects, I think it's completely consistent with what Paul showed in his theoretical descriptions and essentially of adding hydrogen and changes in input. The plot you see there, just make sure you understand what you're looking at. It's furnace data that shows the % decrease in input on the products as you increased hydrogen, and that is true across all of the products. It's not a proportional change, as Paul's plots show, theoretical plots showed. It's lesser than 1%, so it's not a straight percentage, 5% increase in hydrogen, a 5% decrease in input, nothing like that. It's a lesser input change. But despite the differences in the reduction, results were consistent with those predictions, and the influence, essentially in both furnaces and boilers, we tested modulating in stage, two-stage appliances, but these were tested at full rate. So we really didn't evaluate the modulation performance under these different test gases. Everything was done at its full nameplate rate. Next slide, please. In terms of the carbon footprint, which is everybody's looking for, there was the other sort of general observation. We did see across the appliances reduced CO2 emissions, as one would expect, roughly proportional to the percentage hydrogen introduced in the appliance, so fully consistent with the theoretical prediction. But in terms of the air-free carbon monoxides, we saw stable air-free CO despite reductions in CO emissions, and so there's you have to consider how the CO, I think there's some expectation the CO might actually go up on an air-free basis, but we did not see that. We didn't see a problem with CO as CO2 is reduced. But in case of the reduced input, I think the simplest Paul dealt with was that, well, because of the reduced inputs, in order to serve the heat demand of the space, in case space heating, water heating in terms of the hot water requirements, longer operating periods were firing durations required for the same useful heat output. Now, we did not test for that. I think that's a fairly obvious implication of this, but in the case of appliances, that you get a little less in terms of CO2 reductions, and that's really described in the fourth point, is that you do have to increase your firing of fuel gas to achieve the same useful output, and this is neglecting the Paul's implication about some change in efficiency. Even if you hold efficiency or assume it constant, you'll see that you'll have to increase firing rate over time, and that your CO2 reduction on net will be somewhat less than what might be predicted by a simple comparison of the constituents of fuel gas, namely the reduction in methane. I'll comment before we move on to the next slide. All these tests were performed with pure methane. We did not use what we would call wall gas, which would be distributed gas delivered to the testing laboratory. We did that for one specific reason. That was to make sure that we didn't see in the testing operation some change that might be attributable to variability in the supply of the gas. So all gas mixtures were laboratory prepared, certified blends, and certified pure methane for the sake of consistency across the tests. Okay, next slide, please. In terms of the supply implications, the pure methane and hydrogen may not be representative of field performance for that very reason, that we're dealing in the U.S. with a highly variable supply gas situation in terms of other alkanes, other heavier hydrocarbons, and also presence of inerts in the gases that may affect certainly methane number of the gas and Willoughby number as well. So it's essentially the conclusions are really applicable to pure methane and pure methane hydrogen mixtures. And but as far as additional testing, this issue of actual test gas, also actual delivered gas is an issue, particularly in North America. And also this suggestion that out of the white paper that was described earlier, that the standard interchangeability criteria of higher heat value limits may have some limitations in terms of their applicability as we get to higher and higher percentages of hydrogen blends. And then we'll get into that a little bit more, but it's important from the U.S. from the standpoint of the gas quality limits that are imposed on gas suppliers have generally, with the newer tariffs for interstate between states gases, have specification for higher heating value and Willoughby limits. So this applicability of those two metrics for characterizing natural gas hydrogen blends is important, because there may be other issues that need to be taken care of. And not really mentioned in prior presentation from Joseph. I mean, the chief behavior we're concerned about is essentially flashback, which is, it requires more detailed interchangeability criteria to quantitatively evaluate. Next slide, please. In terms of the gas piping testing, again, this is done in terms of looking at pressure decline over time, and then another test looking at essentially bubbles in the water bath. We didn't find any testing when looking at black steel with unions or corrugated stainless steel or copper. In terms of that simple test, there's going to be follow-on to this, but certainly in that simple test for what piping and tubing within the appliances might do, we didn't see any evidence of problems. And so the pressure decay is the second bullet point. Next slide, please. Okay, I turn that back over to Yusuf to wind up the summary of this testing program. Yusuf?
Thanks, Ted. Appreciate that. So as we kind of continue to talk about, there was really no conclusive results based on this research, but there is an abundance of interest to continue assessing safety, performance of the decarbonization strategy across the industry. So it's expected that the results that were delivered to the respective technical committees back in December, they continue to assess that data to determine the path forward. but we will be also publishing the CSA group public report this spring. And just a special thanks to Ted for supporting the development of that report and working with CSA group staff on pulling all the necessary pieces and parts together. As the testing of this exploratory program was winding down, we did receive a proposal from an industry stakeholder that was looking at expanding on this initial step to introduce hydro blends up to 50% or more, include a broader scope of products, and potentially look at also including in-service and used legacy appliances. At this point, CSA is attempting to form a project advisory panel consisting of various stakeholders to help with developing the scope, looking at prioritizing the testing and establishing a total cost. We welcome others that are interested in continuing to further this important work and potentially reach out to me in the future if you have any interest. The exploratory, project provided initial results that are still being evaluated by industry to understand the potential impacts to CSA codes and standards. And as mentioned, continue to mention, further efforts are needed to have a conclusive approach on the matter and look forward to future activity. Thank you very much for the opportunity today, and I hope you enjoy the presentation.
Thanks, Yusuf and Ted. Great presentation. And hey, Ted, your organization represents many energy companies, and so they deliver natural gas throughout the country. So would you spend a few minutes to talk a little bit about the AGA's current activities and plans on this subject?
Absolutely. Yeah, I'd be glad to. Thanks, Udon. With respect to AGA, just as background, AGA represents over 200 local distribution companies across the U.S. And we also coordinated heavily with Canadian Gas Association in Canada, who serves the same function for Canadian utilities, and we do have some activity with hydrogen with Canadian Gas Association. But in terms of where we would like to go with this, I think that our initial proposal for the exploratory program was just to get into this, that we didn't see a lot happening in the U.S. with respect to appliance activity related to adding hydrogen to fuel gas, and needed to get something. And so we wanted to be sure we work with industry and insisted on AHRI being involved with it from that perspective, because we're not going to do anything without manufacturers' involvement, either from the standpoint of appliance design or certification. So, I think as gas suppliers, it's incumbent on us to have that sort of interaction. Just go through a couple points in terms of where we think we're going. This issue I raised earlier about essentially real natural gases as part of natural gas hydrogen blends becomes important, and particularly looking at combustion behavior as it changes when you add the heavier hydrocarbons and inerts to those blends, because we think those are certainly the physical properties of those gases will change, and we're looking more at things like methane number as a metric, and that's used in Europe as a basis for EU exchange of gas cross border. And so it's something we need to look at as well. But certainly, in the sense we need to achieve some consensus for testing purposes on what the represented natural gases are. And from this goes a little bit beyond the current certification test gases, but nevertheless, we want to be sure that the testing we do is represented. And there are some sources coming mainly out of the natural gas vehicle industry that sample gases across the U.S. and has developed essentially some good data that we can use for working on a consensus on what the test gas should be. And what we do with this in terms of appliance testing and certification, I'll talk to one idea of that a little bit later, but it's an open question and something we want to work closely with AHRI and members of AHRI on. With respect to what Paul is referring to in terms of legacy appliances and what we would call legacy technology for appliances, this issue of diffusion flame burners, or so-called Bunsen burner technologies, partially premixed burners requiring secondary air entrainment for complete combustion. And we're talking about certainly cooktops or cooker burners, but certainly in the U.S., we're talking about a large population of what people sort of dismiss as legacy technologies, but nevertheless, we've got in the U.S. over 70 million customers in the residential sector. And all or most of those customers have one or more legacy appliances. And so the issues of operating on what we would call a legacy burner design, which would be, again, the diffusion burner technology, becomes very important. And so we take a very strong look at the issue of how existing installed appliances using this diffusion burner technology would respond to these changes in gas. We did this previously in the early 2000s with respect to gas interchangeability, when the U.S. believed it would be importing large volumes of liquefied natural gas from other countries, very different compositions than U.S. produced gas. And so we're familiar with that sort of challenge of looking at those appliances that are installed using this older technology and the sensitivity of those appliances to changes in fuel gas. Now, we've enlisted the support of Dr. Howard Levinsky, recently retired from DNV GL, formerly University of Groningen, and also Hasuneum in the Netherlands, who's been active in this area for well over 20 years to help us with some of the issues related to burner technologies and how they may respond. And one issue we're taking a look at is really sort of illustrated in Paul's theoretical slide, that as you go out to higher and higher percentages of hydrogen, where is the essentially the empirical basis for the Wobbe number relationship break down? And we're pretty confident that we can define what we think is a reasonable operating range for using the Wobbe metric. But again, because of the U.S. regulatory scheme for gas supply, we need to have a very, and as proposals for higher percentage of hydrogen might come forward, we need to understand what that the value of the Wobbe number alone, or do we need other metrics to essentially characterize this? And based on some data that Dr. Levinsky has provided with respect to cooker burners or range top burners, that suggest that there are some issues at concentrations above 15% hydrogen as far as flashback. And so, and with those burners as well, because we didn't modulate anything in our test program, we are interested in the case of cookers and cooktops, how do consumers modulate their burners? They essentially turn up the input. And so you essentially, to achieve the same boiling rate of water, for example, on a cooktop, what are the implications of that? You're increasing the firing rate, increasing flame temperature off the flame, and doing other things that might have implications that might not be seen in an appliance that has this preset firing rate. And so we're working with Dr. Levinsky and sort of getting some background on what some of those burner experiences are and how they might be important for some of the appliance categories we're interested in. And then this issue of field performance, particularly with respect to pilot ignition, is an important issue for us because it's more than a pilot ignition. We've got in the U.S., at least in terms of shipments, over 40 million unvented space heaters in the U.S. market. Now, how many of those are installed and actually used? It's going to be some lesser number. But nevertheless, they all use not only pilot ignition, but they also use an unstable pilot as part of their ignition device, or their combustion safety system. The oxygen depletion sensor specifically is an unstable pilot, which essentially, as the oxygen is depleted in the environment by design, the pilot becomes unstable such that it doesn't maintain a heat to the thermocouple and the appliance shuts down. So it becomes a safety issue in that category of appliances. And we did see with the one space heater that was tested, some issues in the pilot performance of the space heater. It becomes an issue that may bleed into the issue of safety of the appliances. In terms of near-term appliance testing opportunities, we're looking at the use of used appliances. Joseph had made reference to a proposal that's being issued by a major North American utilities, which will take appliances that have an operating history associated with them into interchangeability tests using natural gas hydrogen blends. And then, of course, cooking appliances, we referred to that earlier. We have a program with Canadian Gas Association under a laboratory program to look at emissions from cooking appliances, combustion emissions. But we'll also be throwing in a natural gas hydrogen blend of 15% to look at changes in performance related to cooking appliances, which have not been part of the exploratory program. And then the last line of the slide is not visible, but it is what do we do as far as test gases in the Z21, Z83 standards. We have a series of test gases that's quite old in those standards, not applied to all appliances, but nevertheless, butane air is one of the test gases. There's a category in the test gases called mixed gases. We've been having conversations with longtime members of the Z2183 technical committee on how we would input a test gas, including natural gas hydrogen blend into the test gas series. And we've got some initial ideas and talked around how that might be introduced. And we're really looking at looking at furnaces might be a good a working group of the Z2183 standard series to start developing proposals for introducing test gases. And I think the consensus coming out of the out of AGA through its hydrogen task force is looking at maybe 15% being the initial proposal for a test gas augmentation for those standards. And so no proposals has been submitted at this point. It's only a discussion, but we're moving forward in that way. One other and final point on standards actions, the LC1 committee is responsible for corrugated stainless steel tubing, is interested and is writing a proposal for AHRI consideration of testing different exterior to the appliance, but interior piping performance with natural gas and hydrogen blends. And in that case, possibly going up as high as qualifying piping systems up to 100% hydrogen. That's a general purpose sort of a gas delivery sort of approach outside of the appliance area, but nevertheless is something that I think the research committee of the AHRI will be seeing in the coming months. So that's all I have. Okay. And thanks for listening. Sorry I took so long.
Well, great. Thanks a lot, Ted. Again, thanks all speakers for the talks. There's definitely a lot of information. Unfortunately, we run out of time. We got a lot of questions going on submitted, and so I think we have maybe just one question. I think I see several attendees ask the purpose of using hydrogen blended fuel because generating hydrogen would consume energy, and what's the overall emission impact and so on. So I think maybe just to clear out the air a little bit, maybe Paul or Ted, and would you like to answer this one?
Paul, you want to take a stab at it first?
Paul, are you on mute?
Yes, hello. Sorry, I'm back. I was trying to answer a few of the questions.
Yeah.
So can you just repeat what you?
Yeah, the question, the purpose using hydrogen blended fuel, because generating hydrogen would consume power and consume energy and generate emission. What's the overall environmental impact? Does Europe have anything study or?
Well, yeah, in the UK, we're obviously surrounded by quite a lot of water, quite a lot of wind turbines, which produce electricity when it's windy, whether you need it or not. So the proposal is when it's in summer, when there's not a high demand for electricity, any surplus wind energy, instead of turning the turbines off, which they have to do now because they can't store the electricity generated, the idea is we'd turn it into hydrogen and simply store it in appropriate places to be used as and when. The alternative, of course, is using carbon capture and storage and methane steam reformers to extract the hydrogen from the methane and pump the CO2 back under the North Sea, because there's huge empty gas fields that we spent the last 30 years emptying of methane that we could now fill up with CO2. So the pure objective is to reduce CO2. They need the most economical way of doing it. And one of the questions I haven't got around to answering is about decarbonisation. Yes, mixing 20% hydrogen doesn't give a 20% decarbonisation, of course. It only actually reduces CO2 by about 6%. But 6% of quite a lot is still quite a lot. And the proposal over here certainly is that the idea of blending is to build up hydrogen capacity, manufacturing capacity, that at some future point it can be switched over. So at the moment, they couldn't just start a hydrogen network. They haven't got enough hydrogen. But if they build up the capacity by blending it into the gas main, then at some point they'll take the blending out and convert maybe Leeds as a first city. And then gradually, as the hydrogen builds up, they'll convert other cities. That's the plan.
Yeah, Paul,
Thank you.
I apologize for throwing that at you. I thought maybe, yeah, given the European and the UK experience, that you might have a little more than we have at the US. But anyway, it's sort of a dirty trick to throw that in your lap, so I apologize. But as far as the US goes, I mean, we talk about this in terms of the various colors of hydrogen, if you will, in terms of sourcing hydrogen supplies and how they might enter the gas system or support on-site power generation or hydrogen pipeline systems. But we talk about gray hydrogen, essentially from fossil fuels, and I don't know all the precise distinctions, except that it's essentially an inferior form of production, but it essentially uses conventional technology to produce hydrogen. We refer to blue hydrogen, which is essentially hydrogen that might be produced from natural gas with carbon sequestration from the production. A little more speculative, a little more costly, a little more process intensive. And then a green hydrogen, which I think is the holy grail that people are looking at, and that's using, as Paul was referring to, the essentially renewable sources, wind and solar, essentially to split water molecules into hydrogen and oxygen, and to use the hydrogen essentially during off-peak power generation times, where people refer to it as sort of the cheapest form of hydrogen production, when you've got these renewable assets spinning, but you don't have need for the electricity they produce. Essentially, hydrolyze water and produce hydrogen that way. All of this requires a compression step, which is an energy-intensive operation, capital-intensive operation. I think some of the economics behind some of these conversion technologies are still shaking out, and what the ultimate cost of the hydrogen will be as a commodity produced. I think everybody believes that in volume that the cost will come down and to be more reasonable to be absorbed by the natural gas costs. But anyway, I think that's my answer.
Yeah, thanks, Ted. One last question for Joseph. Do you have expected start time for potential testing on the legacy equipment? Or still in the stage? Yeah.
Sorry, so yeah, there's no expected timeline right now. Well, I will say I think the expected timeline was initially to start in the fall. Unfortunately, priorities are the priorities for not only CSA, but the stakeholders that were involved in the initial discussions took precedence. So again, I mean, we're trying to identify a solid number of interested stakeholders from all the various categories. So we're looking at from a manufacturing, from regulator, from utilities, and so on to kind of create this advisory panel. So once we have the advisory panel, it's really going to be the initiation to hopefully continue to look at that expanded proposal.
Okay, thank you so much. Great. I guess thanks a lot again, and we have listed all the key point of contact at each organizations for you. And if you have additional thoughts, please contact us. And apology for running a little bit over time, but we will look through your questions and consolidate them and reach out to you. Clearly, there is still a lot of research work to be done, but I can assure you that when you're back home today, your furnace and the water heaters are not burning hydrogen. So can't guarantee tomorrow though, but we thank you all for coming, and we thank our speakers Now this section is concluded. Yeah, enjoy the rest of your day. Bye now. Thanks.
Thank you.